In this video, we're going to take a look at some applications of the exponential functions that we've been looking at already in this chapter. We're going to look at what are called exponential growth and decay models, and we're also going to look at logistic growth models. You'll notice in the book, Newton's law of cooling is also covered in this section, where that's something we're not going to cover. So we're going to look just at the what's called uninhibited growth or exponential decay and logistic growth models. So our objectives in this video are to find equations of populations that obey the law of exponential growth or decay, and to use logistic models. The general formula that describes exponential growth or decay, what's called uninhibited exponential growth, is this pattern right here. You see A of t, the amount after time t, is a sub 0, which is the initial amount or population, times e to the kt, and the value of k is the rate of growth if k is positive, or the rate of decay if k is negative, and it's expressed in decimal form. And then t is in time. T can be in any time units. It could be hours, minutes, seconds, days, months, years, but whatever the label is on t, the label on k should match. So k will be measured in a percent per unit of time. So if t is in hours, k would be percent per hour. If t is in days, k would be in percent per day. The models are going to have graphs that look like this. If k is positive, we'll have what we picture as exponential growth. If k is negative, we'll have what's called exponential decay. We'll have an exponential function that's getting smaller, closer to 0 as time goes on. So our first example here, we're told the number of bacteria present in a culture at time t, in hours, obeys this model. N of t equals 1000 e to the 0.01 times t. So in this example, the model is given. In some upcoming examples, we're going to be given some information, and then we'll have to build the model. But here we just want to take the given model and kind of pick the pieces apart. Our starting question is to determine the number of bacteria at t equals 0 hours. That's the same as A naught, but you can find it by putting 0 in for t. We'll have 1000 equals e to the 0. E to the 0 is just 1, so that's just 1000. But notice if we're looking at A of t equals, or N of t in this case, is the initial value e to the kt. The initial value, which in the general model is usually called A sub 0, but here we might call it N sub 0, would be 1000. So 1000 bacteria initially. The growth rate for the bacteria, that's the K value, 0.01. But so then we want to say the rate of growth is 1%, switch that to a percent, per time unit, which in this case is hours. So pay close attention to the label there. The rate of growth is always a percent per time unit, so here 1% per hour. Graph the function using a graphing calculator. So grab your graphing calculator and make sure you can get this to look the right way. We want to put y equals 1000 e to get to the e to the, you push the second button and then the natural log key, which will bring up an e with an exponent built in. We want to make sure we have 0.01 and x both in the parentheses, so those both get on the exponent. And then for our window, we're talking about time probably being positive here. So let's start with 0 for our input, and then let's go out to even just 10 hours, this will probably grow relatively quickly. Actually, let's do, I don't know, a couple days, 48 hours. Maybe make our scale 4 and then do a zoom fit so that we don't have to think about the y values. So it looks like they're headed upward. It almost looks linear. This is a pretty slow rate of growth. But if we go out to maybe, 100 hours, it'll probably look less linear. Yeah, I can see that curve there then at least. Okay. So we had what looks like an exponential function, but with a fairly slow rate of growth. If we want to know the population after 4 hours, we'd want to plug t in equaling 4. That's an input, so we can go to our second calculate menu, the value when x is 4, and we get 1040.8 roughly. So we would probably want to round down to 1040 because 0.8 doesn't make sense for part of a bacteria. So. And then if we want to know when will the number reach 1700, we can approach this graphically. 1700 would be an output, so a y value. So we would want to graph that line, 1700. Let's check to make sure our window is large enough. Right now we're going up to 2718 for the y's, so that should show up on our graph. So here's that line 1700. We want to find the place where those two lines are equal, so the intersection point. First curve, hit enter. Second curve, hit enter. And it looks like about 53 for the x. So right around 53 hours. So that was graphically, we saw that. Let's also go through this algebraically by hand. So we would set the output equal to 1700. And we want to solve for t, so first we need to get this 1000 out of the way. So divide by 1000. That's going to reduce to what, 1.7. And then we want to take the natural log of both sides. Natural log of 1.7 on the other side. We'll have the natural log of e to this, so that's just going to be 0.01 t. And then divide by 0.01, so t would be natural log of 1.7 divided by 0.01. Grab a calculator. We know what we're expecting, but let's make sure we get the same thing this way too. About 53 again, so 53.06 hours, just like we saw when we graphed it. Then the last question here, when will the number of bacteria double? That's giving us something about the number, so we want to fill in for our output probably 2000. The initial value was 1000. So we could do this by hand and say 2000 equals 1000 e to the 0.01 times t. Divide both sides by 1000 and then we'll have 2 equals e to the 0.01 times t. That means the natural log of 2 would be 0.01 t. So t would be the natural log of 2 divided by 0.01. And we're expecting more than 53 hours because it took 53 hours to get to 1700. So let's make sure that that's true. Natural log of 2 divided by 0.01. About 69.3 hours. So in that example, again, the model was given and we had to answer some questions based on the model. Now we want to be building the model ourselves, given some information about a population. So here we've got the population of a Midwestern city follows the exponential law. That tells us that the number of people after time t is the initial number times e to the kt, and k is either positive or negative. We don't know which. That would be determined after we've got some information about some specific times and populations. So part A says if n is the population and t is the time in years, express n as a function of t. That's what we did right there. They're just looking for that general pattern. And then in the second part, they're asking us to actually find the model and then answer a question. So we first need to find n sub 0, the initial number, find k, and then use those to write a specific model. And then answer the question. So it's kind of just like if we knew this were linear, we would want to find the slope, and then we'd want to find the y-intercept, and then we'd answer a question. Here the pieces we need to fill in are the initial, the rate of growth, and then we'll answer the question. So this is saying the population decreased from 900,000 to 800,000 between 2005 and 2007. So this is going to be a negative k value when we're done. And we can use, looks like 900,000 as the initial. And we also have another ordered pair. Let's see, 2 years after that, the population was 800,000. So with n sub 0 equals 900,000, we can say, well, n of t then is going to be 900,000 e to the kt. And with this pair, we've got 800,000 equals 900,000 e to the 2k. Fill in a 2 for t, and we still don't know k. So we can divide both sides by 900,000. That would give me 8/9 equals e to the 2k. And then we can take the natural log of both sides. So it appears that k will be the natural log of 8/9 divided by 2. So negative 0.05889. The easiest thing to do is to actually store that in your calculator. So to store a value, instead of rounding it, you can push STO and then arrow, which is right above the on key. So store, and then let's call that K. To get the K, which is right above the left parentheses, you push the alpha key, and then that parentheses button, and then that would store that as K. So just hit enter. And then we'll write down the approximate value here, 0.05889, negative 0.05889. And then we can update our model. N of t is 900,000, e to the roughly negative 0.05889 t. And then if we want to know what the population is going to be in 2009, that's 4 years after the start. So n of 4 would be 900,000 e to the negative 0.05889 times 4. Or you can use the stored k in your calculator as the, as k here. So we could do 900,000 times e to the, let's pull up that k, times 4. So it looks like about 711,111. So this was using the stored k on calculator. So if we round that number, we'll come up with something slightly different. So if we actually do 900,000 e to the negative 0.05889 times 4, it's close to the same, but we get a little bit more because we chopped off that decimal a little bit early, so we wouldn't be decaying quite as quickly. Right. So the more exact you can be, the better. So storing that on your calculator instead of rounding it is a little bit better. So our rate of decay, even though they didn't ask, we'd say the rate of decay would be, what, 5.889% per year, because time was in years. The next thing we want to talk about is called the half-life of a decaying, something that's decaying. So like carbon is often talked about as having a half-life, but any substance that's decaying exponentially, we can talk about the time required for half of it to decay, and that's what is referred to as the half-life. So we'll find a general rule for figuring out what the half-life is or how it's related to the K value. So what we want to do here is figure out how is K related to the half-life. That's our question. So when we're at the half-life, we've got half of the original amount left. So we'd have the amount left would be half of a sub 0. So we would set up the equation 1/2 of a sub 0 equals a sub 0 e to the kt. To figure out what k is here and how it's related to t, we would first divide by a sub 0. So we'd have just 1/2 equals e to the kt. Then we'd take the natural log, so we'd have the natural log of 1/2 equals kt. And the k value then would be the natural log of 1/2 divided by t, where t is the half-life. Using laws of logarithms, we could say that's the same as -1 times the natural log of 2 divided by t, because 1/2 is the same as 2 with the exponent -1, and the exponent can be moved in front. So you'll see that formula written either of these ways. They're equivalent, but they look a little different. So if the half-life is t, you can figure out k by using this formula, natural log of 1/2 divided by the half-life, or -1 times the natural log of 2 divided by the half-life. So in example 3 here, if they give us the half-life, 1.3 billion years, we can use that to find k. We can say k then is going to be negative natural log of 2 divided by 1.3 billion. And definitely on that one, that's going to be a really small number, so you just want to store that as k on your calculator. So natural log of, so let's do negative natural log of 2 divided by 1,300 Whoops, and then another 3 zeros, and then another 3 zeros. So store that as k. Alright, so I'm going to take a screenshot of that so we can look at it later. So that's our K value. And then if 10 grams are present now, that means that A sub 0 is 10. How much will be present in 100 years? So we want to figure out A of 100, when the input is 100, would be 10 e to the k times 100, where k is this number over here that's stored in our calculator. So we'll make a note, use k from the calculator. Right. And let's see what we get. So we want 10 times e to the k times 100. So it looks like really just only a tiny bit less than we have right now. But still it is a little less, so that many grams. The next example is quite similar to the one we just did. We've got a fossilized leaf contains 70% of its normal amount of carbon-14. The half-life of carbon-14 is 5,600 years, and we want to figure out how old is the fossil. So again, we want to start by using the half-life is 5,600, so we can use this to find K. And K would be the opposite of the natural log of 2 over the half-life, which is 5,600. We can store that in our calculator. Store that as K. And then we'll use that to answer the question. So now it says it contains currently 70% of the normal amount of carbon-14. So that means right now, A of t, we don't know the time, but we know that it's 70% of the original, so 0.70 times A naught. So the current output is 0.70 times A naught, and the pattern is A naught e to the k, which is on our calculator, t. So we want to divide by A naught, divide by A naught. We're solving for t here, so 0.7 equals e to the kt. It looks like the natural log of 0.7 would be kt. So t is the natural log of 0.7 divided by k, which is this value that we've stored as k on our calculator. So let's do that. Natural log of 0.7 divided by k. So about 2881.6. And that would be years, because time was in years throughout this problem. All right. Then lastly, we want to look at what's called a logistic model, and we saw this in one of the other videos as well, but here's our general pattern. So if we have a function that looks like this, we've got a constant over 1 plus a e to the negative bt. This is what's called a logistic model. A, b, and c are constants. C is positive. If b is greater than 0, so if there's actually a negative exponent there, then it'll be a growth model. If b is less than 0, so if negative b is actually positive, then you'll have a decay model. The graphs are going to look, they'll have this general shape where they either look like an S like that or an S like that. So this is if b is greater than 0, and if this is b if less than 0. We're never going to have to come up with the model to fit a given set of information here. We'll just be given a logistic model and want to be able to look at the graph and answer some questions about it. But it just helps to know what to expect for the shape of the graph so that you can choose your window so that you're seeing the right shape. So in this example, example 5 here, we've got a model for the companies, the percentage of companies reporting that they used Microsoft Word, where T is the number of years since 1984. Right? And so the growth rate is this value. So this is a large growth rate. We'd say the growth rate is 79.9% per year. Right? And then we want to graph this function. So 99.744 divided by 1 plus 3.01. I lost my plus sign there. E to the negative 0.799 t, or x. For our window, let's do 0 to 25 maybe, just for a span of 25 years. And we can make our scale 5, and then let's do a zoom fit. If we included negative values, we would see that flat part of this graph, but to the left. But here we see this steep rise and then this leveling off. That's characteristic of logistic growth. So there's our graph. We want to know what was the percentage of Microsoft Word users in 1990. So t equals 0 was 1984. So this would be, we want the percent at 6. So let's see the percentage in 1990. Grab your calculator, put in 6 for the input. So calculate the value when x is 6. So 97.3 if we round to the nearest hundredth, 30. So already in 1990, 97.3% of companies were reporting using Microsoft Word. And then during what year did the percentage reach 90%? So that was going to be obviously somewhere before 1990. This was an output value, so we can graph the line through 90. And we can see where those cross each other. Looks like 4.17 roughly years after 1990. So on the graph we saw x was about 4.17. So in about 1988, between 1988 and 1989, let's say between 1988 and 1989, so sometime during 1988. And what is the carrying capacity for this function? That's the value at which the function levels off. So if we look at the table, for example, or even just do a trace. So let's look at the table. So if we go to table, and mine is set automatically to be going up by ones. If yours isn't doing the same thing, you can go to table set and adjust it so that you either are putting in inputs, or if you just scroll down to see where we start to see, it looks like they level off at 99.744. Right? If we could see more decimal places, we could see that these aren't actually exactly the same, but they're the same at least out to the thousands, right? So the carrying capacity would be 99.744%. So we saw this on the table. But we can also think about why this is happening from the formula. One plus 3.01 e to the negative 0.799 t. As t goes to infinity, so as time gets larger and larger, e to the negative 0.799 t is going to be getting smaller and smaller and smaller, so that's going to 0. So we get 99.744 divided by 1 plus 0 as t gets larger and larger and larger, and that's exactly what we saw on our table. So at least we've seen some examples of exponential growth and then one example of a logistic growth situation. Good luck with these problems.